During the next Nexus session, I'm going to provide an orientation and brief overview of an analysis commonly known as mixed models with random effects. These analyses are used to analyze longitudinal data. As you know, if you read the literature, longitudinal research is very common. It involves the repeated measurements of the same variables within the same subjects over time. It's the only design that allows us to make a causal inference from the results of the study, also known as pre-post test, repeated measures designs, as in repeated measures analysis of variance, follow-up studies, and then more recently, and more often, you see the reference to these mixed models I'm going to talk about. Repeated measurements require a slightly different approach from that used with data that are collected independently from different subjects, because the repeated measurements often result in correlations, and most conventional tests assume that the data are independent, and if multiple groups are involved, identically distributed across groups. If this correlation across measurements is not taken into account, the tests result in invalid results and inaccurate conclusions. For illustration, I'm going to use an analysis we completed recently in which 42 subjects were analyzed using 4 repeated measurements, trial 1, 2, 3, and 4 of the King-Divick test, which the goal is to read a series of letters and numbers as quickly as possible, so the lower the score, the better. Graphically, the analysis would look something like this. We have 3 subjects here. Each was measured 4 times. And in these types of studies where the entire study took place in under an hour, so we expect to see what's called an autoregressive pattern of correlation, where observations which are closer together are more highly correlated than observations that are further apart. In a typical analysis, say a repeated measures analysis of variance, we would be analyzing the average or the group means for trial 1, 2, 3, and 4, and it would look something like this. But you can see, if we plot the individual data points and connect them with lines, that not everyone started at the same point on trial 1, but they progressed somewhat differently over time. So in using a repeated measures model analyzing means, we're leaving a lot of data on the table. We aren't modeling all the data that we have. So skipping quickly to the point I want to make in the discussion, we will more typically approach these types of data using something called a generalized linear mixed model with random effects. The generalized linear refers to the fact that we can analyze not only normally distributed interval ratio data, but we also can accommodate categorical, binary, count data, and ordinal data by transforming these data to linear approximations. Mixed refers to the fact that we are analyzing repeated measures on the same subjects, but we also can take into account group differences. So we might look at male versus female, or we might have assigned the subjects to different groups in an experimental design. We can also compare those. And the random effects is really the highlight of the mixed model analysis, where you can customize subjects' data via the y-intercept and slope. The mixed model allows for differing numbers of time points from subject to subject. The time points at which the measurements are taken can be unequal across subjects as well as within subjects. Unlike the repeated measures ANOVA approach, mixed models will allow you to accommodate missing values. And finally, the error terms are customized for each data point within each individual. Mixed models can accommodate the correlation of scores within subject across time periods by modeling each person's data and fitting a regression line to changes in that person's scores over time. And these models, these intercepts and slopes, unlike conventional regression analysis, are not averaged. They are customized on an individual by individual basis. And finally, like repeated measures and regression analysis, we're able to take into account multiple factors in one analysis as well as potential covariates such as age or maybe experience. This is a graphical depiction of data collected from 6 subjects, A through F, across potentially up to, 10 observation periods. And you can see that the data differ considerably based not only on the slope of the progression across time points, but also where the model would theoretically intersect the y-axis if extended to that point. So the result of the study is given, the best fitting regression line is given by the dark line labeled estimated overall group regression line. This is a weighted average of the individually customized regression lines depicted by the dashed lines. So if you look at the regression line for subject A, you can see that it's not at all what we might expect. Given that that subject contributes only 2 time points or 2 observations, we would expect the best fitting line to exactly track the change from time 1 to time 2. And if you look at the other dotted lines, you'll see the same thing. None of them exactly track what one would anticipate given an ordinary least squares regression approach. So what happens with the mixed model approach is that the individualized regression lines are customized based on their relative contribution to the overall model. Subject A contributed only 2 observations, and if you compare that to a subject F who contributed 7 observations, you can see that the regression line for subject F much more closely tracks their actual observations than does that for subject A or subject B. What I'd like to do at the next Nexus meeting is to go into a little more detail on this, provide some background and some intermediate information to make sure we're all on the same page, and then we'll go through this in a little more detail. And I'll attempt to convince you that, in fact, these generalized linear mixed models with random effects are the way to go.